All right, today let's talk about unit cells. A unit cell is a tiny repeating unit that makes up a larger solid structure. And when we're talking about solids, we're talking about this phase of matter with a definite shape, definite volume, so it's fixed, it always takes up the same amount of space. And there's kind of two different categories of solids, crystalline and amorphous. So crystalline have this regular repeating order. It's implied in the crystal part of it that there's some sort of order to it. And amorphous literally means without shape. So an amorphous solid would be something that doesn't have regular repeating order to it. Something like glass, for example. So something that is melted, there isn't that regular kind of crystal structure that gives it this kind of three-dimensionality, this geometric shape, that kind of gives it, that unique shape that you think about when you think about crystals. So amorphous means without shape, so it doesn't have that long-term repeating structure. Now crystals or crystalline structures can be any of the four types of solids. We can kind of use that term sort of loosely, even though we usually think about crystals as ionic compounds. So that's usually the way that we're thinking about it. Although we can also talk about things like ice crystals. So when we're talking about frozen water, that's a molecular solid, and we can talk about its crystal structure as well. So it's kind of one of those catch-all terms that we use. So that could mean any of the four types of solids, just anything that has this orderly repeating order. And the thing that makes up these crystals, this regular repeating order, are what are called unit cells. And so the simplest of the unit cells is just kind of a box, a cube, if you will. And so if we think about a big structure, so I have kind of a model here that you can see. This is a sodium chloride model. So if we look at this, we can kind of see that, if I have different colors that represent different atoms, then we can see that there's, atoms on each of the corners of my cube. And if we think about this overall box making up a larger structure, right, this one unit cell making up my whole structure, then I'll just have a bunch of them repeating all out in, three-dimensional space. So you can kind of see how it would build on itself. And that's really how crystals grow. You have a little seed crystal, and then everything kind of expands out from there. So the simplest of those is just cubic, where you have an atom or an ion on each corner. Now, when I'm defining these different types of unit cells, I use this kind of general axis, where this origin of my axis is going to be this atom right here. Okay, so if we're thinking about this in terms of A, B, and C, then my side lengths in a cube are all going to be equal to each other. So A is equal to B is equal to C. Kind of translating that into our structure here. And then A times B times C would give me my volume of my unit cell here. And then the angles between them can be different things. But in a cube, they're all going to be 90 degrees, right? There's a 90-degree angle here, 90-degree angle here, 90-degree angle there in the base. So all of those angles are equal to each other. By our schematic here, if we look between the axes of A and C, then we have the angle beta. So it's the Greek letter that is the non-letter that you're taking in your axis here. So then between B and C axes, I have angle alpha, which is, Greek A. And then between my axes A and B, I have a Greek gamma. So that's kind of in the surface there in the plane. So in my cubic structure, then my alpha is equal to beta is equal to gamma, and that's equal to a 90-degree angle. And that's what defines my cubic structure. Now, if I start to tweak these things, if I change the side lengths or if I change the angles, then that will give me different unit cells. So at the simplest, there's cubic, and even within cubic and within any of the types of unit cells, there are a number of different variations on that. I cover that in a different video that gets into things like body-centered cubic and face-centered cubic. But for our purposes here in this one, we're just talking about the different types, and this really goes to how are the edge lengths related to each other, and how are the angles related to each other. So there's our cubic. If we increase in complexity with our unit cells here, we end up at tetragonal next. And so you can see the limitations of my three-dimensional art skills here pretty quickly. But hopefully you can kind of see that my edge lengths here along my base, well, the intention anyway is that they're the same length. So my A is equal to B in this case. But you can see that my edge length that's coming out this direction, again using this kind of front corner as my axis point. So here's my A, B, and C. If I'm kind of modeling this and thinking about this in 3 dimensions, then C is obviously a different length than my A and my B. So A is equal to B, but it is not equal to C. I have one side that's different from the others. But even within that, it's still a box. So I still have a right angle here, I have a right angle here, and I have a right angle in the surface of my plane. So I still have my alpha is equal to beta is equal to gamma, and all of those are right angles with 90 degrees. That's called tetragonal unit cell. So that one side is slightly different. And usually it's, the convention is that usually it's kind of the tall one that goes up. It's my C there. But that's not always going to be the case. That's just the way that we tend to draw them. Now again, if we increase in our complexity here, then we end up with an orthorhombic structure. So I really like orthorhombic. When I was doing my grad research, a lot of the crystals I was studying were orthorhombic unit cells. So orthorhombic is, and again, my limitation of my art skills here, if we look at the base of this thing, hopefully you can see that these are 2 different lengths. So my A and my B are different from each other. And then you can see that this tall one here, my C, is also a different length than the other 2. So that means in an orthorhombic crystal, I have an A that isn't equal to B, that isn't equal to C. So all 3 side lengths are different from each other. But in terms of angles, we still have a right angle here, we have a right angle here, and a right angle for our gamma as well. So alpha is equal to beta is equal to gamma, and those are all right angles. So that's orthorhombic. I like to focus on these guys to start off with: cubic, tetragonal, and orthorhombic, because the only thing that's changing is the side lengths. And these are really pretty common crystal structures for a lot of materials. You can get into some weird ones, things like monoclinic, where you have all different side lengths and all crazy wacky angles, etc. But I kind of like to focus on these 3 that all have the 90-degree angles, and then this last one that I'm going to talk about, which is hexagonal. So with hexagonal, and again, it's not easy to see, but let's put this one as my corner here. So here's my A, my B, and my C. For this one, the A and the B are the same length, believe it or not, with my terrible art. A and B are the same length, so I have kind of a square base here, but my top one, my C, is going to be slightly different. And again, I don't know how well you can tell this from my drawing here, but it's supposed to be a little bit taller than the other ones, so it's not equal to C. We have that kind of weirdness there. Now, my A and C, so my beta angle here is still a right angle. Hopefully that's fairly obvious. And then my alpha angle is also a right angle. So my alpha is equal to my beta, and those are both 90 degrees. But the weird thing is this angle in here is different. This is no longer a 90-degree angle. This is now a 120-degree angle. So if we're kind of visualizing that, it would sort of look like if I had my kind of peace sign here and we had 3 parts, right? So if it's kind of like trigonal planar geometry, then it would be a 120-degree angle. And that's really the way that we can kind of visualize these, is if we're putting them all together. So if I have a bunch of these guys, then I can kind of picture how they would fit together. It would look a little bit like this. This coming down here, this here, this here, here, and this guy here, and here. So if we had 3 unit cells together, then it would give us this kind of hexagonal sort of structure, right? So here's my hexagon, not easily visible with the way that I've drawn this. The idea is that this would be your hexagon, and then we can kind of draw in our 3-dimensionality from there. It's close. Now the tricky thing with these is that when we start to visualize them all together, we have these little clusters of them where we'd have 3 of these unit cells together, but then we'd have another cluster that's coming down this way, coming out this way, coming out this way. And that angle then, that 120-degree angle, is going to cause this kind of hexagonal look to it. So that's why they're called hexagonal unit cells, even though the unit cell itself, which is just that original one that I had drawn, isn't itself a hexagon, right? It's a part of a hexagon. It's part of 3 unit cells that make up this kind of hexagonal sort of crystal structure. And you've probably seen crystals that look like this, because if you picture these going up kind of in all dimensions, you could see that we'd have kind of this tower with these facets on it. And you've probably seen crystal structures that look like that with these kind of faces along them, that there's these nice cleavage points that the rocks can go across. I usually think about it in terms of minerals when I'm thinking crystals. So these things, you can see these kind of columnar sort of structures, which is kind of neat. I think it's cool that from this atomic or ionic level, we can predict what the shapes are going to be at a more macro scale. So the things that we see that are visible to us are that shape because of the way that they look on an atomic or ionic level, which is just kind of cool. So like I said, there's some other types of unit cells. For me and my purposes, I like to kind of focus on the 3 main ones that all have 90-degree angles, and then this hexagonal one with that weird 120, because this kind of encompasses a lot of the materials that you'll run into kind of in normal everyday life. Okay, so unit cells, lots of geometry, thinking about angles, picturing these things propagating out in 3 dimensions. Takes a little getting your brain around. If you need any help with that or you have any questions on it, don't hesitate to reach out. Otherwise, I will talk to you again soon.